Hi, in this video we are going to talk about this problem. We are given in-order and pre-order traversals of a binary tree. We need to construct the binary tree. So we need to write a function that takes two arrays as parameters, in and pre. It returns root of the binary tree, constructed binary tree by it, as a return value. Please note that we can construct a binary tree only when in-order traversal is given and one more traversal is given. So we cannot construct a binary tree from pre-order and post-order traversal. We can construct it only from in-order and pre-order combination or in-order and post-order combination. In this question, we are given in-order and pre-order combination, so we can construct the tree. Now, if we see these examples, these are the two traversals given and this is what is expected. If you see this tree, the in-order traversal of this tree is 20, 10, 30 and pre-order traversal is 10, 20, 30. If you see this tree, the in-order traversal is 40, 20, 50, 10, 30 and then 80, 70, 90. So this is what is given to us. Pre-order traversal is 10, 20, 40, 50 and then 30, 70, 80, 90. So these two traversals are given and we need to construct this tree. We need to return root of this tree. Now please pause this video and try to write down a code that returns root of the tree for given two arrays. When you are trying this solution, before writing the code, please take some example arrays, some example input arrays and try to solve it using pen and paper. Let us take a look at this example and construct the required tree manually. Then we'll talk about code and implementation. Let's do a recap of in-order and pre-order traversal. We are given a tree with root, left subtree and right subtree. In in-order traversal, we print the whole left subtree first, then we print root's key, and then we print the right subtree. In pre-order traversal, we first print the root's key, then we print the whole left subtree, then we print the whole right subtree. Let's use this to construct the tree from here. Can we guess the root from these two traversals? Take a look at this, take a look at these arrays and try to guess the root. You can guess the root. It's the first item in your pre-order traversal. You are given pre-order traversal, you can always guess the root. You don't even need in-order traversal for this. So we know 10 is the root of this tree from pre-order traversal. But we do not know from pre-order traversal what is in the left subtree and what is in the right subtree. For that, we need the help of in-order traversal. So we know for sure 10 is the root. Now, how do we know what is in the left side of 10, left subtree of 10 and what is in the right subtree of 10? For that, we search 10 in the in-order traversal and we figure out 10 is here. So we know all these nodes are in the left subtree because left subtree comes before root and then all these nodes are in right subtree. So we know this much. So we know the structure is like this. These 5 keys are in the left subtree and these 3 keys are in the right subtree. Now, how do we know the root of this left subtree? To know the root of left subtree, we can just take a look at the next item in pre-order traversal. If left subtree exists, then root is going to be the next item in the pre-order traversal. So root of this subtree is 20. Because what happens in pre-order traversal, we have root, left, right, and then left subtree again follows the same process recursively. Left subtree is also going to have root first. So we know 20 is the root of this side. Now, how do we know what is in the left side of 20 and what is in the right side of 20? We take use of in-order traversal for this. We search 20 in the in-order traversal and we figure out 40 is on the left side of 20, 60, 50, 70 are on the right side. So we know 40 is the left child of 20 and these 3 items are there in the right child, 60, 50 and 70. So we know left child of 20, which is the next item in pre-order traversal, root of left side. Now what will be the root of right side? For that, we can again see which of these 3 items comes first in the pre-order traversal. So we have 3 items. The first that comes first is 50. So 50 is the root of right side. Now what is in the left side of 50 and what is in the right side? For that we take use of in-order traversal. We search for 50 and we know 60 is in the left side of 50 and 70 is in the right side, right? So 60 goes on the left side and 70 goes on the right side. So we have constructed the left subtree of 10. Let us see how do we construct the right subtree. So for right subtree, we have three keys, 80, 100 and 30. Out of these three keys, which key appears first in the preorder traversal? 80, 100 and 30. So 30 appears first in the preorder traversal. So we know 30 is the root. 30 is the root of this right subtree. Now how do we know which part is in the left subtree and which part is in the right subtree? For that, we search 30 in the in-order traversal part and we figure out on the right of 30 there is nothing. So right child of 30 is empty and 80 and 100 are in the left side of 30. So we have 80 and 100 here. So we have two keys here in the left side of 30 and right side is empty. Now out of these two keys, which one is the root of the left side? For that we again use preorder traversal. Which one of these two appears first in the preorder traversal? 80 appears first. So we know 80 is the root of left side. Now 100 comes on left of 80 or right of 80. To figure out that, we again use in-order traversal. So we notice that 100 is on the right side of 80. So 100 is as a right child of 80. So that's how we construct the required tree. This is our tree. We can do in-order traversal of this and pre-order traversal of this, and we can see in-order traversal is going to be this and pre-order traversal is going to be this. Here is one more example for you. Please pause this video and construct the tree for this example. Let us now construct the tree. From pre-order traversal, we know 10 is the root. Now what is going to be in the left side of this 10? There is only one item on the left side, so we know 20 is on the left side. Now what is going to be the root of the right side? We have three items on the right side, 30, 40, 50. Out of these three items, 30 appears first in the preorder traversal. So 30 is going to be the root of the right side. Now how do we know what is in the left of 30, what is in the right? We look for 30 in the in-order traversal. We know 40 is on the left and 50 is on the right. So 40 goes in the left side and 50 goes in the right side. So that's the tree. You can do in-order traversal and pre-order traversals of this tree and you can notice that they turn out to be these traversals. So we've talked about some examples to get basic idea of tree construction. It is strongly recommended that you pause this video now and try implementing a function that takes in-order and pre-order arrays as input and returns root of the binary tree as output. The idea of implementation is we construct the tree in pre-order fashion. We already have the pre-order traversal, right? So we maintain a pre-index variable and we construct the node by just incrementing the pre-index one by one. So if we see this example where we are given in-order traversal as this and pre-order traversal is this, we are first going to construct the node 10 and then we are going to decide what is in the left of it and what is in the right of it by using in-order traversal. And then we are going to construct the node 20, right? And then we are going to decide what is in the left of 20 and what is in the right of 20 by again using in-order traversal. Then we are going to construct 30, then 40 and then 50. So we are going to follow pre-order traversal, and if you look at these codes, they are simply following pre-order traversal. They are first constructing the root from the pre-order traversal, then they are constructing the left subtree and right subtree. Whatever recursive calls of left subtree and right subtree return, they assign these return values as roots left and right children respectively. So what are we doing here? We take the next item from the pre-order traversal. We have a pre-index variable which tells us what is the next item to be picked from the pre-order traversal, and this pre-index variable has to be shared among all the functions so that the recursive calls can also update the same variable. So we take the next item from the pre-order traversal and then we increment the pre-index. So if you take a look at this first line here and this line here in the Java code, what are we doing? We are taking the item at pre-index from pre-order traversal from pre-array and then we are incrementing pre-index. So we have postfix pre-index plus plus, which returns the old value and then increments it. So we just take the current value, constructs a node. After constructing the node, we need to figure out what is in the left side of it and what is in the right side of it. For that, we search this item for which we have built the root. We search it in the in-order traversal. So we have the code, right, to search the item for which we have built the node, which is root arrow key or root dot key. We search it in in-order traversal. We simply search it in the in array. We find its index and store it in a variable called inIndex. So we have index of it in the in-order traversal. Now we know what is there in the left subtree and what is there in the right subtree. How do we know? The values from starting index to inIndex minus 1 are in the left subtree, and the values from inIndex plus 1 to end index are in the right subtree. Because we know that current pre-index is the root of this tree, and to know the left and right, we search this root in the in-order traversal. Whatever is in the left side of this new root, we have this as a left subtree, and whatever is in the right side of this root, we have it as a right subtree. So if we just see this example, what are we doing here in this code? We are first constructing 10, then we are searching 10 in the in-order traversal, right? And when we find this 10 in in-order traversal, we get its index as 1, right? So what are we doing? We are recursively calling this tree traversal for this left subtree of in-order and right subtree of this in-order, right? These are the in start and in end indexes. Initially, we pass in start as 0 and in end as length of array minus 1, which is 4. And initially, our pre-index is 0. So we begin our execution from the first line. In start is not greater than in end. We construct the root node with value 10, which is the first item in pre-order traversal, and then we increment the pre-index as 1. So after you construct the root, you make the pre-index as 1. And after constructing the root node, you search it in in-order traversal. So you find the in-index as 1. Because 10 is present at index 1. Now what are we doing? We are simply saying 10 arrow left is the subtree that you recursively construct from this array and the next item from pre-order traversal, and subtree that you construct from this array and next set of items from pre-order traversal. See, we do not have to maintain start and end indexes of the pre-order traversal because we are constructing the tree itself in pre-order traversal. So whenever you construct the next item, it's going to be the next item of pre-order traversal, right? So we are simply maintaining pre-index variable for pre-order traversal and simply incrementing it by 1. So when you make this recursive call for the left subtree and the control begins in the recursive call from the first line, what happens is you pick the next item in pre-order traversal. You consider the item at current pre-index, which is 1, and then you increment the pre-index to 2, and you pick this item. And this is going to be the root of left side, right? So you make it as root of left side, right? And in the recursion, when you return back, it's going to be linked also. So you make it as root of left side, and after making it root of left side, you search it in the in-order traversal and you find the index as 0. So what you do now, you make recursive calls for left of it and right of it. So when you make recursive calls, these ranges in start and in end, they are going to cross each other. So you will get null and null for left of it and right of it, right? And this is how this subtree is constructed, left subtree is constructed. Now the control comes back to the parent call, the main call, which had constructed 10 and now 20 is also constructed, and it calls for the right subtree. When it calls for the right subtree, what happens? You pick the next item from pre-order traversal because your pre-index must have become 2 by now, because when 20 was constructed, pre-index was updated to pre-index plus plus here, right? It was done pre-index plus plus. So what you do, you pick the next item from pre-order traversal and you make it root of this tree, right subtree, right? Now to decide the left of this route and right of this route, what you do, you search this 30 in order traversal in the given range. So when you search for 30, you get the index as this index. Now you recursively call for this range and for this range in the left and right subtrees of 30. And when you recursively call for left and right subtree, what happens is you pick the next item from pre-order traversal. So your next item is 40. So 40 becomes the left side of 30. And the control goes back to the parent caller because 40 left and right are null. They'll fall into this base case and they'll return null. Now the control goes back to the caller and caller picks the next item from pre-order traversal and next item is 50. So 50 is picked and 50 is constructed and you get the 50 as right child of 30. So this is how your tree is constructed using this code. For better understanding of recursion, I have written in start and in end values for the recursive calls. These are the initial values when you call it for the main tree, right? Your pre-index is initially 0 and in start is the index of first element and in end is index of last element. So these are the values of IS and IE. When you search this 10, you find this 10 at this index, in index becomes 1 and you call for the left subtree with these indexes. You know, your in index -1 is 0, that's what you call for the left side. And in index +1, which is 2, that is what you pass as IS on the right side and in end remains same on the right side. That's how you make the recursive call on the right side. And similarly, 30 is searched in the subtree. It is found at index 3 and you pass in index -1 as the IE on the left call and in index +1 as IS on the right call. So left call gets 2, and right calls get 4. When you make recursive calls for left and right of these, what will you pass? You will see 20 at index 0. So you are going to pass in start as 0 and in end as 0 -1. So you are going to fall into this case for the left subtree of 20. So you are going to get null. Similarly, you are going to get null for right subtree, null for left subtree of this, null for right subtree of this, null for left subtree of this, null for right subtree of this. And that's how this tree is constructed. Let me just do a recap of what we have discussed so far. We have discussed implementation, and in implementation we are constructing the tree in pre-order traversal. We are just maintaining a pre-index variable. And what are we doing with this pre-index variable? We pick the next item from pre-order traversal, make it the root, and then search it in Inorder traversal and find the left side of it and right side of it, recursively construct the left subtree and right subtree, and then connect these left subtrees and right subtrees with the root and then return the root. And this is where we make connection, root arrow left or root dot left or root dot right. We connect these with the return roots of the left and right calls. What is the time complexity of the solution? In this solution, we are constructing the tree in pre-order fashion. We construct the root, then we construct the root of left child, then we construct the whole left subtree. So for every construction, we need big O of 1 time to create the node, but there is some work that we are doing in a loop, which is upper bounded by big O of n, which n is the number of nodes in the tree. So if we want to find an upper bound on time complexity, we say it's big O of n square. This solution takes big O of n square time because for every node, we are doing big O of n work. Can you think of a solution that works in big O of n time? The idea is based on hashing. With hashing, we can reduce this function to big O of n. What we can do is, we can store Inorder traversal keys as key in the hash table and their indexes as value. So instead of linearly searching Inorder array for finding the index of a key, we can just do a lookup in the hash table. So this hash table can be done as a part of pre-processing, and this hash table can be passed as a parameter to these functions so that these functions can quickly figure out what is the index of this item in the Inorder traversal. With hashing, we get big O of n time. And how do we achieve hashing? We simply pre-process this Inorder array, store the keys of Inorder array as keys in the hash table, indexes as values. In C++, we can create an unordered set and we can pass it in the recursive calls. In Java implementation, we can create a hash set and we can pass it around in all the recursive calls so that these recursive calls can find the index of a key in in-order traversal.